Dr. Brian Lacki here, who's working with Paul Thompson in Ohio State University. He's going to submit his PhD in summer this year, and he also got an offer to come here as a postdoc. So yeah, he will be telling us about cosmic rays and sound from galaxies.
Okay. Thank you for having me here. So this is my work on cosmic rays and star-forming galaxies, and these cosmic rays are responsible for the emission from star-forming galaxies at the highest and the lowest energies in the radio and in the gamma rays. So you have M82, and on the left you see it in radio. In radio it's resolved. This is the sort of inner starburst region of M82, and in addition to point sources, which you can see, which are supernova remnants in M82. You also have most of the radio emission comes from this diffuse flow of cosmic ray electrons moving into magnetic fields of M82. So, whereas on the right you see it M82 in gamma rays, which has only been detected just this basically a year and a half ago now, and it's not resolved, but these gamma rays, we think, tell us about the cosmic ray protons in M82. So between the two, you get an idea of what the cosmic rays are doing in M82. So this talk will cover basically three of our papers. We have some more recent papers dealing with the X-ray emission from M82. So these cosmic rays are emitting, in fact, at pretty much all wavelengths, but it's just that they can get buried by brighter things like stars in the traditional optical infrared wavelengths. And we also have a letter on the radio background and comparing that to the gamma ray background, both of which may come from cosmic rays. Okay, so the title of my talk is the ends of the rainbow, so I figured I'd start off by dissecting a rainbow. So this is the cosmic SED, the spectrum of the universe. We see the big bump in the middle here at microwave frequencies. That's, of course, the CMB. And you see a couple of other bumps. So these are the infrared, optical, and X-ray backgrounds. So the CMB dominates the electromagnetic radiation of the universe. At the infrared wavelengths, what we're seeing is sort of the dust-obscured star formation. So you have starlight, and it's happening in dusty gas. The dust absorbs the starlight, heats up, and then re-emits that radiation in the infrared. At the optical and UV wavelengths, you have a background from unobscured starlight. So that's basically you just look up in the sky, you see stars, but you sum that over all the galaxies in the universe. In the X-rays, that's probably dominated by AGNs. You have basically light from accretion disks gets cupped and upscattered by hot gas around AGNs. So that produces much of the X-ray background. So these comprise the thermal backgrounds, basically hot gas, and producing this emission. And the X-ray is sort of semi-thermal. The photons are being upscattered by thermal electrons, although the Compton upscattering process itself is a bit non-thermal. But at the highest and lowest energies, you have non-thermal emission. So there's nothing in the universe that's hot enough to produce GeV gamma rays, as with black body emission anyway. So these backgrounds come from non-thermal processes from cosmic rays. So these backgrounds, the sources of these backgrounds are a lot more mysterious. Radio background, we think, comes from star-forming galaxies. We're not actually sure about the strength of and normalization of the extragalactic radio background. But we expect at least some to be star-forming galaxies, and there might also be an AGN contribution. Gamma rays are a bit more mysterious. There's definitely contribution from AGNs, from blazars. It's not clear how much it might be all of it, might be some. Star-forming galaxies might also contribute to these gamma ray backgrounds. You might also have more exotic processes involving ultra-high energy cosmic rays emitting radiation as they travel through the universe. Foreground pulsars in the Milky Way, dark matter, or something we haven't even thought of. And at the very lowest frequencies, at like the kilohertz, we don't really have any reason to suspect there's anything there, but if there is, it's some kind of plasma process would have to be the source of that. So cosmic rays are responsible for the radio and possibly gamma ray emission of the universe. We measure them at Earth, so the cosmic rays at lower energies, they mainly consist of protons and some heavy nuclei. There are electrons, but they're a lot less numerous. So the proton from about a GeV to a PeV in energy we think are galactic. The protons at much higher energy are probably extragalactic, and in between we're not so sure where that transition is. So we measure them at Earth, but we also know that they pervade the Milky Way. So at the top we have the gamma ray emission of the galaxy, and here it's basically the cosmic ray protons lighting up the gas of the Milky Way. So the protons collide with interstellar gas atoms. They produce unstable particles called pions, and these decay into gamma rays and other particles. On the bottom, we also know that there are cosmic ray electrons throughout the galaxy. These move through the magnetic fields of the galaxy and produce synchrotron radiation, which are, so we know that there are both magnetic fields and cosmic ray electrons throughout the galaxy as well. So the importance of these cosmic rays is, for one thing, they can pervade the ISM, unlike, say, ultraviolet light. So they can penetrate deep into molecular clouds. And the lower energy cosmic rays drive the chemistry of molecular clouds. It's also been supposed that they provide feedback of some sort, regulating the amount of star formation in the galaxy. So these cosmic rays are related to star formation, we think. And in fact, people use the radio emission, which comes from cosmic ray electrons, as a star formation tracer. And I will be describing that has something to do with, it has to do with the far-infrared radio correlation, which it hasn't been explained fully. And finally, these cosmic rays from star formation processes, perhaps including supernova remnants and other processes, these are sort of the background for more exotic processes like dark matter. So it's been, people look for dark matter by looking for anomalous cosmic rays from as the dark matter decays or annihilates with itself. But you have this sort of sea of electrons and positrons and protons competing with it from normal mundane star forming processes. So we have to understand this sort of background to them to get at the more exotic stuff. So in other galaxies, until recently, the only galaxy detected in gamma rays was the LMC. So the only real handle we had on cosmic rays in these other star-forming galaxies is through their radio emission, which is a lot easier to detect. And in fact, we find that for star-forming galaxies, we observe a linear and very tight correlation between infrared and radio luminosities. This is called the far-infrared radio correlation. It spans a very vast range of parameters. Galaxies like the Milky Way rely on it, but so do starburst galaxies, and even the most intense starbursts called Eulers, the ultraluminous infrared galaxies. They, in fact, fly with a bit more scatter, but they still follow the basic trend of the correlation. The correlation is basically linear, except that at low luminosities for the more dwarfy type galaxies, where it starts to break down a bit. So people, in fact, use this as a star formation tracer So whereas infrared you might need a space mission to measure the star formation rate of a distant galaxy, you can just use ground-based radio. But this synchrotron emission is connected to both the magnetic fields and the cosmic ray population of the galaxy. So how could this thing work? So this correlation has been observed for about 40 years now, and our explanation of it is still incomplete. So this first notes back in 1973. This is an early paper, but with IRAS, they found with IRAS, you start to get a big sample of galaxies, and by the 90s, it was known that thousands of galaxies lie in this correlation, except for these down here, which are more, we think, are AGNs. So it's basically linear. You'll see plots like this a lot. So this is the ratio of far infrared to radio. And you'll notice that it's basically constant across, in this case, luminosity. So
that ratio is logarithmic or what?
this is logarithmic. It has a constant to it, but basically the gigahertz radio emission is about 1 million times fainter than the total infrared emission. And we now know that the correlation appears to hold for most galaxies out to pretty high redshift of about 2. And with newer instruments like EVLA, hope to push this out to higher redshift. And so these are more brighter galaxies you can see at redshift, at the higher redshifts. But with EVLA, we might be able to detect fainter things like the Milky Way out at higher redshift. And again, you see this sort of constant far infrared to radio ratio. So the scatter in this correlation is about a factor of 2. So it's pretty tight, actually.
So I'm not sure I see it's a factor of 2. What's it like?
In this plot, so this is most of the things lie within perhaps about 0.3. When do you actually? So this is
Okay.
exactly
Point.
Okay. The higher redshift measurements have a bit higher scatter. And so one of the most impressive things about this correlation is the sheer range of conditions where it applies to it. So it works for the normal galaxies, like our own Milky Way, where things are pretty quiescent. So you're forming just a few stars per year, and the magnetic fields are pretty weak, just a few microgauss. The gas that these cosmic rays are traveling through is pretty rarefied. It's basically just less than 1 atom per cubic centimeter. And again, the radiation field is also pretty weak. But it also works for example, the Starburst core M82. And that galaxy is forming several stars per year in a region that's a lot smaller than the Milky Way. That's just basically a kiloparsec in diameter or less. And the magnetic fields we think in these galaxies, in these starbursts, are quite a bit stronger, as we'll see. Perhaps 10 times stronger, 10 or 20 times stronger than in the Milky Way. The radiation field is a couple of 100 times stronger than the Milky Way. And the gas, the average gas density is a couple 100 times stronger than, or higher than in the Milky Way. And it even works pretty well for the correlation even works pretty well for the densest starburst cores of the ULERTs like R220, the nearest ULERT. So the starburst cores of these things are forming, we think, like 100 stars per year in regions just 100 parsecs just across. The magnetic fields are little gauss, we think. Their radiation fields are tens of thousands of times stronger than in the Milky Way. And similarly, the gas density is about 10,000 times that of the Milky Way. And yet, the physics seems to work out for all these kinds of galaxies, so that the cosmic ray electrons are somehow working with the magnetic fields to produce this constant radio emission with respect to the infrared. So this sheer range of physical conditions begs for a simple explanation of the correlation. And that explanation was proposed about 20 years ago. It's called calorimetry. So it's basically the simplest explanation for the far-infrared radio correlation. And the idea is that, so young massive stars are the sources of both the infrared radiation and the cosmic rays. So we've just assumed that these young massive stars are producing UV light, and then all of that UV light gets absorbed by dust. And then all of that radiation gets re-emitted in the far infrared. These same young massive stars, they undergo supernova explosions. The explosions, the shocks of these explosions accelerate cosmic rays. And if they do so at a constant efficiency, they'll produce just some fraction of their energy will go into cosmic ray electrons. And then we just assume that all of that machine goes into radio. So basically, because all the starlight goes into far infrared light and all of the cosmic ray electrons go into radio, you get this constant ratio across all galaxies. But is it really that simple? The physics of cosmic rays electrons is very complex. So in the Milky Way, we think that they can escape the galactic disk, and they basically diffuse off of plasma waves in the galactic halo, and then they eventually escape. In Starbursts, there are also huge winds that can just advect or basically just convey the cosmic ray electrons out. The cosmic ray electrons can cool also and emit synchrotron radio waves, but they can also scatter off ambient starlight and produce gamma rays through the inverse Compton process. Finally, in the denser galaxies, the cosmic ray electrons can actually collide with gas atoms themselves and emit radiation. And so they can either hit an atom and then knock off one of its electrons, so it can ionize an atom, or the cosmic ray electron can sort of be deflected in the electric field of an atom and emit bremsstrahlung radiation. So all of these processes are sort of competing for the power going into the cosmic ray electrons. And while the four processes on the left have been considered to some extent in previous models of the far infrared radio correlation, the ones on the right, the bremsstrahlung and ionization, where the cosmic rays are interacting with gas atoms, those haven't really been explored all too much until recently. The other complication is the fact that there are cosmic ray protons. And the cosmic ray protons, in fact, dominate most of the energy going into cosmic rays by a factor of about 100, at least in the Milky Way, we think. And the problem there is that the cosmic ray protons can also hit protons or atoms in the interstellar medium. And when they hit these atoms, they produce the unstable pions, which in turn decay into the gamma rays and the neutrinos, and also neutrinos, but they can also produce electrons and positrons directly that way. So you have this additional source of electrons and positrons from protons hitting gas atoms. And this process may be very efficient in environments with dense gas, perhaps including starburst galaxies. So what we'd like to do is to understand how these processes work in the galaxies across the far infrared radio correlation. And the way to understand how cosmic rays live and die in these galaxies is through the diffusion-loss equation. It has a number of terms. This governs the evolution of cosmic ray spectra in the galaxies. We did the simplest thing that might work. So we're considering basically a one-zone model of the galaxy. So that means we get rid of the spatial terms. So we assume that, and we basically lump all of the escape terms into a sort of a lifetime. So we assume that the cosmic rays are either in a galaxy or starburst, or and then eventually they die and they just escape. You also can have the cosmic rays can lose energy through radiation, so as they cool by interacting with these other processes, and something's putting in cosmic rays into a galaxy. And finally, we assume that the cosmic ray spectrum is in equilibrium, which should be a pretty good approximation for normal galaxies and the stronger starbursts, because the time scales of those processes is relatively short compared to the evolutionary time of a galaxy. There's a much simpler way to understand what we're doing here. So basically what we're saying is that the cosmic rays are being put in a galaxy at some rate, that's this Q term, and then they live for some time, and then that gives you the spectrum. So now all of these terms are energy dependent. So the lifetimes depend on energy. So for example, synchrotron emission, the radio emission, that becomes stronger at higher energies, whereas ionization is stronger at lower energies. So the relative strengths of these processes determines what this final spectrum will be. And in our models, we need some sort of gas density. So we parameterize with the gas surface density. And then we use the Schmidt law to get the star formation rate from that gas surface density. So the star formation rate in turn gives us the rate at which cosmic rays are being put into a galaxy, and also the amount of radiation that's being so that for inverse Compton losses. A key feature of our models is that so normal galaxies, we observe that the cosmic rays fill up a region that's about a kiloparsec or so in scale height, perhaps a little bigger in fact. So they kind of diffuse a bit through the halo. Whereas with starburst galaxies, most of the radio emission comes from thin disks, just about a few hundred parsecs wide, and only about 100 parsecs or less in thickness. So the starbursts we observe are a lot more compact and thinner. And finally, the big unknown here is the magnetic field strength, which we think, or which we parameterize as going at some power of the density. And what we do is so first of all, you have three main unknown parameters here. We have the efficiency that the cosmic rays electrons are being accelerated. That comes, we constrain that with the sort of normalization of the radio emission, the normalization of the correlation. You also have the strength at which the protons are being accelerated, and we basically normalize that with respect to the Milky Way, where we have a bit more information. So we basically use the gamma ray luminosity of the Milky Way to set how many protons there are. And then finally, there's magnetic field strength. And that's set by basically whether the correlation is linear or not. So this is what a model looks like. So this is
what does the A get out of that tuning process?
As we'll see, it's 0.7 if you scale with respect to gas surface density, or if it's if you go with volume density, then it's 0.5 or 0.6. So this is an example of our models for a low density galaxy, a bit like the Milky Way. So you have protons, they dominate, and then you have primary electrons. And finally, you have these secondary electrons and positrons being created by the protons, but they're very weak. And that's pretty much what we see in the Milky Way. But if you look at one of these high density starbursts like R220, first of all, you can see that there are a lot more protons. The more surprising thing is that you can see the secondary electrons and positrons in our models actually dominate the primaries. So that's unlike what we have in the Milky Way. Okay.
Sorry, that was after everything escaped, or where is this? I mean, you have a steady state model. I mean, if that's not what sets the
so most of the
slope, I guess.
Yeah, so the slope, okay, so in the low density galaxies, these slopes are mainly set by escape, especially the relevant energies. That basically sets the light time, so cosmic rays just escape. Whereas in these high density galaxies, as we'll see, in fact, cosmic rays in our models can't escape. So it's mostly set by the radiation processes. And in fact, the slope is a bit, for the protons, is a bit flatter or harder because escape in the Milky Way is an energy-dependent process, whereas the loss process isn't. And so what happens if we set the magnetic field strength to evolve very strongly with gas surfaces? Well, then we find that the far-infrared radio correlation is broken, so you don't get this constant ratio anymore. In fact, we find that these galaxies with high gas surface density are very radio bright, and so you don't. If you have the magnetic field be too weak in the high-density starbursts, then the reverse happens. The galaxies, the high-density galaxies, the electrons aren't producing enough synchrotron radio emission, and radio emission becomes too faint, and they become the correlation is broken again. So instead of this constant line, you have this broken correlation. Where it works is, in fact, for if the magnetic field strength goes as the surface density to the 0.7 power. And so this, as you can see in our models, it basically get this constant ratio. So we do find a solution, even with all these extra processes. The properties of the solutions are a bit interesting. So in the Milky Way, the cosmic rays, the magnetic field, and the starlight are roughly in equipartition with each other, and also with the gas pressure. Because we're using the Schmidt law, we find the radiation, the cosmic rays, also sort of track each other up till for the normal galaxies. And for this magnetic field dependence, the magnetic field energy density also scales with the radiation field. So it's like the radiation and the magnetic fields are in equipartition. Where this starts to break down is for the highest density starbursts. So we see that the cosmic rays here, they sort of fall behind the radiation and the magnetic fields. And the reason is basically because the protons are crashing into the gas atoms, and they're losing energy and producing these gamma rays and neutrinos, which just escape without contributing to the pressure. So these radiation losses are significantly reducing the amount of cosmic rays in starburst galaxies, although the pressure is still pretty high compared to the Milky Way. So does this calorimetry explanation work in our models? Yes, but it's a bit complicated. So for normal galaxies, in fact, calorimetry fails. So basically, not all the UV light gets absorbed, but some of it just escapes into the interstellar, out of the galaxy. And so you might expect that as the radio emission, as the ultraviolet emission just escapes, you get less infrared emission. But what happens in these lowest density galaxies is that the cosmic ray electrons, they also escape their host galaxies. So the galaxies are also underluminous in radio emission. So both the infrared and the radio emission sort of fall away at roughly the same rate for these lowest density galaxies. And in fact, so those two effects kind of cancel each other out. And this is, whereas in these high density starbursts, neither the UV nor the cosmic ray electrons can escape. So they're trapped, and you have calorimetry.
Sure. It almost looks like you'd still get what you'd
expect to get more scatter on the low end.
Yeah,
And
in
on the
fact,
high end, that you in fact see the opposite, don't you? I mean, you see more scatter in the starbursts.
in Euler's you do see
Yeah.
more scatter, but also at the low end of the correlation, you do also start to see scatter and nonlinearity. So that does suggest, in fact, that this correlation is breaking down, that something's breaking down.
Okay, so, well, I guess, since I already asked. So but I mean, so what's the scatter on the high end then, do you think?
I'll be getting into that, but it's not as simple as I'm making it out here.
Sure.
So basically, in calorimetry, you have no free parameters, and that's the beauty of it. Now, if you just included cosmic ray escape, or just ultraviolet escape, the correlation would be broken, and things would get out of balance. But since they both start to happen at the low density end at about the same time, the things balance each other out to some extent. Now, studies of the infrared emission of galaxies do support the fact that there's, by Bell 2003, do support the fact that there is, in fact, infrared emission escaping from these low density galaxies. And in fact, the infrared stops tracing the star formation rate. And again, the correlation becomes nonlinear. So that makes sense. But you remember I said that that at the high end you have this these protons are dying and producing these pionic losses. So when they crash into gas atoms, one of the things they produce is secondary electrons and positrons. So you have this additional source of electrons and positrons, and so where's the radio emission from all these other electrons? So as it turns out, we think in our models there's another conspiracy. This one applying just to the starbursts. So again, in normal calorimetry, you'd have no free parameters. As it turns out, though, you have these other loss processes, these other ways that electrons can lose energy through Bremsstrahlung, ionization, and inverse Compton losses, basically by interacting with the gas or radiation in a galaxy. And these processes basically take energy away from the electrons. They kill the electrons before they can radiate radio. So they so with just those processes, these galaxies will become radio faint. But on the other hand, the protons are sort of coming in and producing more electrons and positrons. And these electrons and positrons sort of produce the remaining radio emission. These two processes come out to balance each other out. This conspiracy in our models is pretty large, in fact. It's an order of magnitude, which is very surprising. And yet, it seems to work. So I know what you're thinking. Okay, I'm having this huge conspiracy, which somehow works to keep the ratio of radio emission to infrared emission in these galaxies working. So how could that be? Well, on the secondary, on the proton side, the reason this may work is that the protons, at least in the Milky Way, they're about 100 times more. There's about 100 times more energy in protons than in electrons. And as it turns out, if these protons are being efficiently destroyed by these pionic losses, then about 1/6 of that energy goes into these electrons and positrons. So you might expect that something like you might expect that if the protons are being efficiently converted into these pionic losses, that you'd expect about 10 times more secondary electrons than primaries, unlike Milky Way. It gets a bit more complicated for different spectral slopes, but the basic idea is the same. So you might expect that to enhance it by the radio emission by a factor of 10. On the other side, you have these non-supertron losses. And so the size of the starburst is here a key factor. So in the Milky Way and other normal quiescent star-forming galaxies. The radio emission comes from a region that's that's kiloparsec in scale height, whereas in these dense starburst galaxies, the scale height is only about it's only about 100 parsecs tall. So basically, you're taking the same gas surface density, but you're compressing it into a region that's 10 times smaller, so you have a 10 times higher gas density. And gas density is what sets the strength of the Bremsstrahlung and ionization. So Bremsstrahlung and ionization would be, 10 times stronger. And so you get those two factors of 10. But there's something else we have to check. We have to check that once you do get this factor of 10, then that it's preserved. The ratio of these other loss processes to synchrotron is preserved for the starbursts. So that basically you want the fraction of energy going into synchrotron with respect to these other loss processes to be constant. And so basically, it all comes down to this gas surface density dependence on the magnetic field strength. So the Schmidt law says that basically that the radiation field goes as gas surface density to the 1.4 power. And with this magnetic field strength, the ratio of the magnetic fields to the radiation is constant. So the inverse constant from the radiation is the ratio of that to the synchrotron stays the same from one starburst to the other. And what's less expected is that the ratio of Bremsstrahlung to synchrotron also remains constant. And the reason for this is because we're observing a constant frequency instead of energy. So basically the ratio stays the same. So basically the Bremsstrahlung goes as density, whereas the synchrotron goes at a given frequency goes as e to the 3/2. So if you have d, so d goes basically as density to the 2/3, and then you take it to the 3/2. It cancels out with the density. So the ratio of Bremsstrahlung to synchrotron remains constant. Ionization is it doesn't cancel out as well, but it's most important for the highest density starburst, which is also where we see the bigger scatter in the correlation. So basically in our picture, summing up, in the starburst, you have most of the UV light does get absorbed and it comes out in the infrared. And the cosmic ray electrons are trapped, but a lot of the emission of their power goes into gamma rays and other loss processes. But you also, these same supernova that accelerate the electrons are also accelerating protons, which create the secondary electrons, and these come in and produce more of the radio emission. So what we'd like to do is to test this conspiracy. And one way to do this is to try to unbalance it. One thing we can do is try to go to higher redshift. So at higher redshift, the CMB is much stronger. And you might think that with a much stronger CMB, you'd have additional inverse constant losses off this higher, stronger CMB. And that would change the balance of these loss processes. So basically, it comes down to the ratio of synchrotron, the synchrotron cooling lifetime with respect to all the other, to the basically total lifetime of the cosmic ray electrons. So it's not just a simple competition between the synchrotron and the CMB now, but also you have all these other loss processes that also are working. And what we find in our models is that if you try to go to higher redshift, we find basically that this conspiracy actually preserves the Parameterize radio correlation. So in the older view, you just had synchrotron and the CMB, and the problem with this is, and then as the CMB got stronger, it would overwhelm the synchrotron, so the energy would go into the inverse competence, and it would basically suck all the energy away from the cosmic ray electrons, and then these galaxies would become radio faint, and then the correlation would basically be broken at high redshift. But in our models, you have all these other loss processes which dominate over synchrotron. So the CMB is just a small portion of the total balance of these, the total balance of the cooling processes in these galaxies. And so we find that these other loss processes sort of buffer the correlation. They actually preserve it to very high redshifts. And so in our models, at redshift 0, you have this sort of constant ratio of radio to infrared. And then if you go out to a very high, to redshift 4, for example, the dimmer normal galaxies, which don't have this correlation, this conspiracy, they do become radio faint. But on the other hand, these high density galaxies, the CMB does pretty much nothing to these galaxies. They should still be on the RER radio correlation. But there's another way we can try to break the correlation, and that's to, and so, as I was saying, the reason why this conspiracy works in our models is because basically the starbursts are very compact. They're very thin. You have this, the gas has a small scale height. But there are starbursts out there at high redshift which are not compact, which are spread over galactic scales, and these are the submillimeter galaxies. You can see them in radio telescopes that their radio emissions coming from regions are kiloparsecs across. These are still pretty intense starbursts forming sometimes hundreds or even thousands of stars per year. And what we find also is that they're dynamically hot. So you have wide velocity dispersions, which suggests that they have high disk scale heights, about a kiloparsec high. So what that means, though, is that if these things are homogeneous, which is a bit iffy, but if these things are homogeneous, the gas volume density will be low because you're taking a certain column of gas and you're stretching it over a very high, long height, scale height. And so that, in our models, that should unbalance the conspiracy, depending on how the magnetic fields go. So if the magnetic fields are strong, instead of this balanced conspiracy, you basically knock away the Bremsstrahlung and ionization because the gas density is low in these galaxies. And so what you instead have is, so you have more energy and power available for synchrotron radio. And so what that means is that these galaxies can be radio bright in our models by a factor of about 2 to 5 in some of our models. Again, depending on how the magnetic field strength goes. So in our models, what we find, so these are the galaxies we observe at redshift 0, but so basically in our models, these are the sort of puppy or the puppy starbursts, including the submillimeter galaxies. And you see that they're radio bright by a factor of a few. And now the interesting thing here is that there have been observations claiming that submillimeter galaxies are in fact radio bright by a factor of 3. So instead of relying on this correlation here that we observe at redshift 0, these submillimeter selected galaxies appear to be radio bright. And in normal calorimetry, there are no free parameters, so you can't explain it. But in our models, you basically have this. You have these other loss processes which can be adjusted, and you can sort of unbalance the conspiracy. Now, this is still not settled because these measurements depend on what the shape of the far infrared SED looks like, and that's been a bit hard to fit. In this paper, the Galaxies et al., they do try to fit the entire SED using many measurements of the infrared spectrum, but it's pretty hard. The final way we could try to look at these things is to look for the gamma rays. So if you really do have these secondary electron and positrons, you must also have pionic gamma rays. So when the protons produce these pions, in addition to these electrons and positrons, they also produce neutrinos and gamma rays. Now, until recently, we've only detected the Milky Way and the LMC, but just a year and a half ago, we've detected 2 and now 4 starbursts, MA2, NGC 253, and these 2, which are also C-bursts, 49, 45, and 1068. So with these gamma ray detections, you can now finally talk about what the protons are doing in these galaxies. These MA2 and NGC 253 are also these are Fermi measurements here in GeV gamma rays, but these 2 have also been detected in TeV gamma rays as well. So one thing we can do is we can say, so we now know basically the gamma ray luminosity of these galaxies. And we think we know what the cosmic ray luminosity, the power going into cosmic rays, because we have some idea of what the supernova rate is, and also what and we can, if we assume that the cosmic rays are as efficiently being accelerated as in the Milky Way, then we know what the power going into cosmic rays is. So you can basically just take the ratio of power going into gamma rays to the total power in cosmic rays, and that will give you some idea of how much power is in fact being lost by these protons to these pionic processes, and how much instead is being escaping. So when we take this ratio, our best estimates are that MA2, basically a third to a half, or somewhere in that range, some of that much energy is in cosmic rays is being lost into these pionic processes. Whereas in the Milky Way, that number would be just a few %. So it appears that pionic losses are about an order of magnitude stronger in M82 than in the Milky Way. So that's not this perfect proton calorimetry, as we call it, this perfect. So these radiation losses aren't perfect, possibly because M82 has big winds that are sort of carrying the cosmic rays in bulk out of the galaxy, but we do seem to have quite a few gamma rays and then we assume secondary electrons and positrons. NGC 253 is a bit more unclear because the supernova rate isn't as well known and the detection is fainter, so we don't know the luminosity as well. But our best estimate is that about 1/4 of the energy injected into cosmic rays gets destroyed by these pionic processes, or converted.
So is this LCR coming from the supernova rate, or is it a star formation rate measured independently, and then you assume the supernova rate?
Yeah, we tried 2 things. We first tried the supernova rate of 0.1 supernova per year, which is basically a common value in the literature, but there's high scatter in that. The other thing we tried was to use the infrared luminosity. So the infrared luminosity gives you basically, so that comes from the young, bright, massive stars, and we convert that into a supernova rate. So what we find is that these galaxies are gamma ray bright with respect to MA2 and NGC2. So these galaxies are radio bright with respect to the Milky Way. And there does seem to be this, so this is GeV gamma ray luminosity with respect to the basically star formation rate. So this is sort of a color here, and gamma ray bright things are up here, whereas gamma ray dim things are down here. So one thing we expect in our models is that this ratio of gamma ray luminosity to star formation rate should basically asymptote at these highest densities. And basically, basically because you have this calorimetry effect. So for protons, basically, all their loss processes just produce pions. So you can't get this kind of conspiracy. So at the highest densities, you might expect something like the original calorimetry theory, but for protons instead of electrons. And you might expect the gamma ray far-infrared correlation at these highest densities. But there are just too few galaxies observed yet to really tell for sure. One interesting galaxy to look out for would be ARC-220. It's not hugely gamma ray bright, and we expect that the upper limits will come down and land somewhere in the vicinity, so it has the same gamma ray to star formation rate ratio as these other starbursts. But until we get a detection, we can't say for sure. So the final thing we can do with these gamma ray detections is, okay, we now know that there are these gamma rays, so there must be these secondary electrons and positrons. So that gives you a luminosity in secondary electrons and positrons. You can then compare that to the actual observed radioluminosity. And what we find is that the secondary electrons and positrons, they must be produced at with basically the power being injected in them is basically 10 times the radioluminosity of Na2 and NGC253. So that suggests that there's basically only a tenth of the power going into electrons and positrons at gigahertz at these GeV energies is being converted into synchrotron emission. So that suggests that there are, in fact, these other loss processes in these galaxies operating and suppressing the radio emission. So to finish up, so we modeled sort of the galaxies across this correlation. We found this magnetic field strength, which goes sort of in equipetition with radiation in order to get this linear far-infrared radio correlation. And so at low gas densities for the weakest galaxies, you have these calorimetry breaks down, and you have electrons escaping, and the galaxies aren't opaque to infrared light or to UV light. But at higher energies, you have these higher densities, you have this calorimetry effect. And in fact, that starbursts are too good at being calorimeters, so the protons are also dying and producing these secondary electrons, but these extra radio emission is being suppressed by these other loss processes. So in our models, you have these conspiracies. And we looked at ways that we could break these conspiracies by going to higher redshift, and we find that in fact, the conspiracies preserve the correlation at higher redshift. But also by looking at submillimeter galaxies, which have different physical conditions than the normal compact starbursts we observe at lower redshift, and that might break the conspiracy. Finally, we could look at gamma rays, and we find that you do have significant gamma ray emission from these starburst galaxies, perhaps a bit lower than in our models, but we still have strong pionic losses in these galaxies, and also the radio emission is very weak compared to the gamma ray emission, which implies you have this other, you have some other loss process suppressing the radio emission of these galaxies. So thank you.
I guess there's time for
Any thoughts about why the magnetic field is scalar?
Yeah, that's an interesting question. So it's not in equipetition with what you'd expect for the midplane hydrostatic pressure, and it's not. And it's also so we don't really understand this well.
But it is in equipartition.
With radiation,
With
yes.
radiation.
Todd thinks that maybe the radiation is driving some kind of turbulence, and if that's happening, then the turbulence generates the magnetic field. So if the radiation So then you might expect the radiation, the magnetic field to scale with the radiation. But at the moment, we don't understand it. The other thing is that instead of gas surface density, you could go as gas volume density. In that case, we find it goes basically as the square root of gas volume density. And we do observe something similar in galactic molecular clouds. So maybe that would, in that case, our conclusions for the submillimeter galaxies are different, but you have weaker magnetic fields, but perhaps it has something to do with that.
So for you guys' model, will ARC 220 be observed by Fermi or in the PV anytime soon? Or?
So it's difficult because, well, Fermi has already been up there for 2 years. So even if, now if it gets an extended mission of 10 years, you can push it down by a factor of 3. But even then, it's challenging. On the other hand, at the TeV end, there is the planned Cherenkov telescope array, which is supposed to be very strong, and in that case, we do expect it to be detected eventually.
Okay, I guess we finish and go for cookies upstairs. Right around